Module 9, Lecture B, BFS and DFS. By the end of this lecture, you will be able to implement BFS and DFS traversals on graph structures in Python, apply BFS to find shortest paths in unweighted graphs, and DFS to explore connectivity or detect cycles, and analyze the time and space complexity of BFS and DFS in terms of vertices and edges. Breadth-first search. Queue-based BFS. Breadth-first search explores a graph level by level, starting from a chosen vertex and visiting all vertices in order of increasing distance from that start. It uses a queue to manage this process. You mark the starting vertex as discovered, place it in the queue, then repeatedly remove the front vertex and examine its neighbors. Any neighbor that has not yet been discovered is marked and added to the back of the queue. This systematic use of a queue ensures that all vertices are visited in the correct breadth-first order. In breadth-first search, the queue is essential because it controls the order in which nodes are explored. Unlike a stack or recursion, which drive depth-first search by following one path deeply before backtracking, the queue makes you explore all nearby nodes first. For example, in a social network, starting from one person, the queue ensures you visit direct friends before moving on to friends of friends, and then further connections. In this way, the queue holds the search frontier and processes vertices in the order they are discovered, preserving the layered structure of the exploration. To implement breadth-first search, you typically need three main parts: a graph representation, a way to mark visited vertices, and a queue. The graph is often stored as an adjacency list, while a separate structure tracks which vertices have already been discovered. The queue manages the order of exploration, starting from an initial vertex and then visiting its neighbors layer by layer. This method gives a clear, predictable traversal and is useful in tasks like exploring web pages, planning routes, or modeling how information spreads. Python code, queue-based BFS. This material explains how breadth-first search works on a simple graph using a queue. It shows that vertices are visited level by level, starting from a chosen point and moving outward. The process uses a queue to manage which vertex to visit next. It also reports the order in which vertices are visited and how the queue changes over time to illustrate the characteristic behavior of breadth-first search. This line explains that the script uses only Python's built-in standard libraries and does not depend on any external packages. This matters because it means you can run the code without installing anything extra. As a result, the script is easier to use, more accessible, and straightforward to execute on most systems that already have Python installed. We can represent a simple graph using a dictionary as an adjacency list, where each key is a vertex and its value is a list of neighboring vertices. For instance, one vertex might connect to two others, and another vertex might connect back to the first and to additional vertices. This setup lets us quickly find and traverse each vertex's neighbors by looking them up in the dictionary. The adjacency list format is especially efficient for sparse graphs, where most vertices are not connected to every other vertex. We use the deque structure from the collections module to build an efficient queue. A deque lets us quickly add and remove items from both the front and the back. This is especially useful for breadth-first search, where elements must be processed in the order they were added. By using a deque, we can maintain this first-in, first-out behavior efficiently. We define a function that performs a breadth-first search on a graph using a queue starting from a given vertex. The function takes the starting vertex and the graph as inputs. It creates a set called visited to record which vertices have already been discovered. This prevents revisiting the same nodes and allows the search to move through the graph efficiently. To begin a breadth-first search, we create a queue using a double-ended structure that lets us efficiently add and remove items from both ends. We then place the starting vertex into this queue as the first node to explore. At the same time, we add this starting vertex to a visited set so we do not process it again later. This setup initializes the traversal by tracking both where we have already been and which vertices we will visit next. We keep a list called visit order to record the sequence in which vertices are explored during a breadth-first search. As the algorithm runs, each vertex is added to this list when it is visited. When the search is finished, this list clearly shows the traversal order through the graph. The code uses a loop that runs as long as the queue still has items, ensuring that all reachable vertices are processed. In each iteration, it removes the vertex at the front of the queue, following the first-in, first-out behavior of a queue. That vertex is then added to the visit order list, which records the sequence in which vertices are visited during the traversal. This line of output shows which vertex is currently being visited and the contents of the queue at that moment. By printing both pieces of information, it makes the breadth-first search process easier to follow. You can see the order in which vertices are processed and which ones are waiting to be visited next. This helps you understand how the queue changes over time during the traversal. The code goes through each neighbor of the current vertex using the graph's adjacency list. For every neighbor, it checks whether that vertex has already been visited. If it has not, the algorithm marks it as visited and adds it to the queue so it will be processed later. By repeatedly doing this, the algorithm explores the graph in a breadth-first way, visiting all vertices level by level before moving deeper. At the end of the breadth-first search, the function returns a list of vertices in the order they were visited. This list is the final output of the traversal. It shows the exact sequence in which each vertex was explored during the search. In other words, it summarizes the path the algorithm followed through the graph. We run a breadth-first search, starting from vertex A on our graph. This search visits A first, then explores all vertices directly connected to A, and then continues outward level by level. As the algorithm visits each vertex, it records the visit in order. This recorded sequence shows the exact order in which the vertices are explored using breadth-first search. The code outputs the final order in which vertices were visited during the breadth-first search. This visit order is stored in a list that was filled as the algorithm ran. Printing this list shows the exact sequence of visits and clearly illustrates the breadth-first nature of the traversal. In other words, It provides a concise summary of how the algorithm explored the graph. This script shows how breadth-first search works on a graph using a queue. The graph is stored as an adjacency list, and the traversal begins at vertex A. The algorithm visits vertices level by level, always exploring all neighbors of the current vertex before moving on. A queue keeps track of which vertices to visit next by adding unvisited neighbors in order. During the process, the script prints the current vertex and the queue contents, and in the end, it outputs the full order in which vertices were visited to illustrate the breadth-first behavior. Layered graph exploration. Breadth-first search explores a graph in layers, moving step by step outward from a starting vertex. It visits all vertices at the current distance before moving on to those that are one step farther away. This guarantees that closer vertices are processed first and that the order of exploration directly reflects their distance from the start. As a result, breadth-first search naturally reveals both the exploration order and the shortest number of steps from the starting point to each reachable vertex. In breadth-first search, it helps to think of the graph in layers based on distance from the starting vertex. The queue manages these layers by taking a vertex from the front and adding all its unvisited neighbors to the back, which builds the next layer. As this continues, the current layer is gradually removed while the next layer is filled. This process repeats until all vertices are discovered, ensuring they are processed in order of increasing distance from the start. Breadth-first search explores a graph in layers based on distance from a starting point. In a social network, it first visits a person's direct friends, then friends of friends, and continues outward, revealing degrees of separation. In a transportation network, it similarly finds cities reachable in one hop, then 2 hops, and so on. By organizing vertices into these distance-based layers, breadth-first search clarifies the traversal order and the relationships between connected vertices. Python code. Layered graph exploration. Use a simple friendship graph to demonstrate how breadth-first search explores a network in layers. Starting from one person, show which friends are discovered at distance 1, which appear at distance 2, and so on. Clearly list the vertices in each distance layer, so listeners can see how the search moves outward step by step. Connect this layered structure to the behavior of the queue in breadth-first search, emphasizing how it creates ripple-like waves of discovery through the graph. The commented line mentions installing Network X, Matplotlib, and Seaborn. But the note explains that these libraries are not actually needed for this script. It is probably left over from an earlier version or a hint for possible future improvements. In its current form, the script performs all graph operations using basic Python data structures. As a result, it has no external library dependencies. We represent a simple undirected friendship graph using adjacency lists stored in a dictionary. Each person is a key, and the value is a list of their friends. For example, Alice's list includes Bob and Carol, and Bob's list includes Alice, Dave, and Eve. Because each friendship appears in both people's lists, this structure makes it easy to see and explore how individuals are connected in the graph. We start the breadth-first search by choosing Alice as the initial vertex. From this starting point, the algorithm explores the graph layer by layer, first visiting Alice's direct connections and then moving outward to their connections. The chosen starting vertex is important because it defines where the search begins and how it spreads through the network. To begin a breadth-first search, we create a visited set that initially contains only the starting vertex, Alice, so we can track which nodes have already been explored. We also create a queue that starts with Alice as its first element to control the order in which nodes are processed. Using the visited set prevents us from revisiting nodes, and using the queue ensures we explore nodes level by level. Starting with Alice in both structures sets up the search to expand systematically to her neighbors. During a breadth-first search, we use a dictionary to record each vertex and the distance layer at which it is first discovered. We begin by assigning the starting vertex, Alice, a distance of 0. This marks her as the origin of the search and provides a reference point for measuring how far other vertices are from her in terms of search layers. In a breadth-first search, we repeatedly process items from a queue as long as it is not empty. We remove the first item, treat it as the current vertex, and then look at each of its neighbors. For each neighbor that has not been visited yet, we mark it as visited, add it to the queue so we can explore it later, and assign it a layer or distance that is one more than the current vertex's layer. This way, we systematically explore the graph and track how far each vertex is from the starting point. We create an empty dictionary that will map each layer number or distance from the starting point to a list of vertices. Then we go through each vertex and its distance and use a method that creates an empty list for a distance if it is not already present. For each vertex, we add it to the list that corresponds to its distance. In this way, all vertices are grouped by their distance layer, making them easy to access and display later. We begin by stating that the breadth-first search starts from Alice, which sets the stage for the results that follow. Then we go through each distance layer in order, using the layer to vertices dictionary to find which vertices were discovered at each distance. For every layer, we sort the names alphabetically and join them into a single, comma-separated string. Finally, we output the layer number together with its list of names, giving a clear, structured view of the exploration order and how many steps each vertex is from Alice. This script shows how breadth-first search works on a simple, undirected friendship graph. Starting from Alice, it explores friends layer by layer, based on their distance from her. As it runs, it marks which nodes have been visited and assigns each one to a layer according to how many steps away it is from Alice. The output lists these layers in order, making it clear how nodes are discovered and how many degrees of separation they have from the starting point. Unweighted shortest paths. Breadth-first search can be used to find shortest paths in an unweighted graph because it explores vertices in expanding layers from a starting point. When every edge has the same cost, the shortest path is simply the one with the fewest edges. As the search visits each new vertex, the first time it arrives there is guaranteed to use the minimum number of edges. By recording how each vertex is reached, breadth-first search effectively becomes a shortest path algorithm, similar to finding the quickest route in a city where every road takes the same time to travel. To find shortest paths with breadth-first search, you enhance the algorithm by recording two things for each vertex: its distance from the start and its predecessor. As you visit each new neighbor, you set its distance to one more than the current vertex and store the current vertex as its predecessor. When the search finishes, every reachable vertex has a shortest path distance and a link back toward the start. To recover the path to a target, you follow these predecessor links backward from the target to the start, then reverse that sequence. This works because breadth-first search always discovers vertices in order of increasing path length. Breadth-first search is useful for finding shortest paths in unweighted graphs, where all connections have the same cost. It can reveal the minimum number of introductions between two people in a social network, the fewest moves needed to win a board game or puzzle, or the smallest number of hops in a communication network. Implemented with adjacency lists in Python, it tracks both distances and predecessors, so it can return not only the length of the shortest path, but also the exact sequence of steps, while keeping the efficiency of standard breadth-first search. Python code, unweighted shortest paths. We use breadth-first search to find shortest paths in an unweighted graph modeled as city intersections connected by equal-length road segments. Each edge represents 1 mile, so the distance between intersections is the number of road segments on the path. Starting from a chosen intersection, breadth-first search explores all neighbors level by level to compute the minimum number of segments to every reachable intersection. From this search tree, we can reconstruct and print one shortest path from the start to any target intersection, along with the corresponding distances from the starting point. The commented line suggests installing external libraries such as NetworkX, Matplotlib, and Seaborn, but the current code does not actually need them to run. This comment is likely left over from an earlier version or meant as a note for possible future improvements. For the script as it is now, installing these libraries is unnecessary and can be skipped. A simple graph in Python can be represented with an adjacency list, where each dictionary key is a vertex and its value is a list of vertices directly connected to it. For instance, one vertex might be connected to two others, and this pattern is repeated for all vertices. This structure makes it easy to access neighbors and traverse the graph, which is important for algorithms such as breadth-first search. The graph is unweighted, so every edge has the same cost or distance, which simplifies finding shortest paths. To begin a breadth-first search for shortest paths, we first choose a starting vertex in the graph. In this example, we select vertex A as the starting intersection. This choice defines where the algorithm begins exploring the graph layer by layer. From this starting point, all distances and paths to other vertices are measured and calculated. We use the deque class from the collections module to create a double-ended queue, which lets us efficiently add and remove elements from both the front and the back. In breadth-first search, this structure is used to manage the queue of vertices we still need to explore. It allows quick access and updates to the list of nodes as we move through the graph, making the traversal more efficient. We begin by creating a dictionary called distance to record how far each vertex is from the starting point in the graph. At first, we set the distance for every vertex to none, meaning no vertices have been discovered yet in the breadth-first search. As we explore the graph, we update these entries to show how many edges away each vertex is from the start. This lets us track the progress of the search and know the shortest distance from the starting vertex to every other vertex we reach. We start by creating a dictionary called predecessor that records the previous vertex for each vertex in the graph. At the beginning of the algorithm, every vertex is assigned a predecessor value of none, meaning no connections are known yet. This setup is essential for breadth-first search because, after the search finishes, it lets us trace back from a target vertex through its predecessors to reconstruct the shortest path. We start the breadth-first search by creating a queue using a double-ended queue structure and placing the starting vertex A into it. This queue controls the order in which we visit vertices in the graph. Beginning with A ensures that we explore outward from this point layer by layer. As a result, we can systematically track and discover the shortest paths from A to all other reachable vertices in the graph. We set the distance of the starting vertex to 0 to show that it is 0 edges away from itself and to create a reference point for all other distances. This initialization is the first step in breadth-first search. From this starting value, the algorithm can then explore the graph and compute the shortest path in terms of number of edges from the start to every other vertex. In breadth-first search, we repeatedly process vertices from a queue until it is empty. Each time, we remove the first vertex in the queue and treat it as the current vertex. For every neighbor of this vertex, we check whether it has been visited by seeing if its distance is still unset. If it is unvisited, we set its distance to one more than the current vertex's distance, record the current vertex as its predecessor for later path reconstruction, and add the neighbor to the queue. This gradually explores vertices layer by layer until all reachable vertices have been visited. To reconstruct the shortest path after a breadth-first search, we use the recorded predecessors to trace backward from the target to the start. We begin with the target, repeatedly move to its predecessor, and add each vertex to a list until there is no predecessor left. We then reverse this list so it runs from the start vertex to the target. Finally, we check that the first vertex in the list is actually the start. If it is not, we return no path, and if it is, we return the list as the shortest path from start to target. We choose a specific intersection, labeled F, as our target because it marks the endpoint for the shortest path we want to find from the starting point. Defining this target is essential for guiding the breadth-first search process. Once the search is complete, we use the stored predecessor information to trace back from F to the start and reconstruct the shortest path. We reconstruct the shortest path from the start vertex to the target vertex by using the predecessor links recorded during the breadth-first search. A path reconstruction function is called with the start, the target, and the predecessor dictionary. This function works backward from the target to the start, following each predecessor to build the path step by step. The completed path is then stored in a variable so it can be used or displayed later. We now output the shortest path from the starting vertex to the target vertex. This path is reconstructed using the predecessor links recorded during the breadth-first search. The result is a sequence of vertices that shows the route with the fewest edges. Each edge represents a road segment of equal length between two intersections. So this sequence corresponds to the shortest route in terms of the number of segments traveled. We now announce that we are about to print the distances from the starting vertex to every other vertex in the graph. These distances represent the minimum number of road segments, or edges, needed to travel from the starting point to each intersection. Presenting this information provides a clear summary of the shortest path results that were computed earlier in the code. It helps you see, at a glance, how far each intersection is from the starting location in terms of edge count. We go through each vertex in the graph in alphabetical order, so the results appear in a consistent sequence. For every vertex, we report its label and its distance from the starting intersection. This distance is the smallest number of road segments, or edges, needed to reach that vertex from the start. Presenting these distances lets us see the shortest path results produced by the breadth-first search algorithm. This script shows how to find shortest paths in an unweighted graph using breadth-first search. The graph models city intersections connected by equal-length roads, and the algorithm starts from intersection A to compute the minimum number of road segments needed to reach every other intersection. It uses a queue to explore intersections layer by layer, recording both distances and which intersection led to each one. After the search, it reconstructs the shortest route from A to F using these predecessor records. The final output reports that path and the distance from A to each intersection, demonstrating an efficient method for shortest paths in unweighted graphs. Depth-first search. Recursive versus iterative DFS. Depth-first search can be implemented either recursively or iteratively using a stack. In the recursive version, a function visits a starting node, marks it, and then calls itself on each unvisited neighbor, relying on the language's call stack to remember the path. In the iterative version, you manage your own stack by pushing the starting node, repeatedly popping a node to process it, and pushing its unvisited neighbors. Both approaches explore the graph deeply along each path before backtracking, but one uses the built-in call stack, while the other uses an explicit stack in your code. When choosing between recursive and iterative depth-first search, focus on their trade-offs for real-world graphs. Recursive versions are shorter and easier to read, which makes them useful for teaching and quick prototypes, but they can fail on very long paths because of recursion limits. Iterative versions use an explicit stack stored on the heap, so they avoid these limits and handle deeper or more complex graphs more reliably. For large structures like social networks, software dependencies, or financial and organizational graphs, the iterative approach is usually more robust. When choosing between recursive and iterative depth-first search, the main trade-off is between clarity and control. Iterative depth-first search uses an explicit stack, which gives you fine control over how you process neighbors and manage extra information, making it easier to plug into complex systems. Recursive depth-first search is often simpler to write and reason about, especially for problems that naturally break into subproblems, such as finding connected components. Both approaches are valid, and with experience, you will switch between them, recognizing that they are just two ways to implement the same depth-first exploration. Python code, recursive versus iterative DFS. In this lesson, we will run depth-first search on a small graph using both recursive and iterative approaches. We will compare how the system's call stack in the recursive version mirrors the behavior of a manually managed stack in the iterative version. As we explore the graph, we will track and print the order in which nodes are visited for each implementation. This will highlight that despite different implementations, both methods can produce the same visit order and rely on similar stack-based logic. The commented line mentions installing NetworkX, Matplotlib, and Seaborn, but the comment also explains that these libraries are not actually needed for the code to run. This means the code is self-contained and does not depend on any external libraries for its execution. The comment is likely a leftover note or a suggestion for optional graph visualization, but in this context, you can safely ignore it and do not need to install those packages. We represent a simple undirected graph using adjacency lists stored in a dictionary, where each node is a key and its value is a list of neighboring nodes. For instance, node A might be connected to nodes B and C, while node B connects to nodes A, D, and E. This structure makes it easy to look up which nodes are connected and to move from one node to another. That ability to quickly access and traverse neighbors is essential for implementing depth-first search and similar graph algorithms. In this graph representation, we use a dictionary where each node is a key and its value is a list of neighboring nodes. Node D is connected to node B, showing a direct path between them. Node E is connected to both B and F, so it has two neighbors. Node F connects to C and E, completing this part of the network. This structure makes it straightforward to traverse the graph using depth-first search. In a recursive depth-first search, we define a function that relies on Python's call stack to manage the recursion. It takes the current node, a set of visited nodes, and a list that records the visit order. The function first marks the current node as visited so it is not processed again, then adds it to the order list to capture the sequence of exploration. From there, it recursively explores each neighbor of the current node, allowing the entire graph to be traversed. In this stage of recursive depth-first search, we look at each neighbor of the current node and check whether it has already been visited. If a neighbor has not been visited, we call the depth-first search function again, using that neighbor as the new current node. This recursive process continues, moving deeper through the graph until every node that can be reached from the starting point has been visited. In iterative depth-first search, we define a function that starts from a given node and explores the graph using an explicit stack. Inside this function, we create a set to record which nodes have already been visited, so we do not process any node more than once. We also maintain a list to store the order in which nodes are visited during the search. With these structures in place, the algorithm can systematically explore the graph one node at a time. We begin by placing the starting node on a stack, which we use to keep track of which nodes to visit next, similar to how a recursive call stack works. While the stack is not empty, we repeatedly remove the most recently added node and treat it as the current node to process. Before processing, we check whether this node has already been visited. If it has, we skip it and continue with the next node. This approach ensures each node is processed only once, avoiding infinite loops and unnecessary repeated work. In this depth-first search process, each node is first marked as visited and then added to a list that records the order in which nodes are explored. The algorithm then looks at the node's neighbors in reverse order so that, when they are pushed onto the stack, they will later be processed in the original order. For every neighbor that has not yet been visited, the algorithm adds it to the stack, allowing the search to continue moving deeper through the graph. The function finishes by returning a list that records the order in which nodes were visited during the iterative depth-first search. This list shows the exact sequence of nodes as they were explored. It can then be used to examine or compare the traversal order with other search methods or different implementations of depth-first search. To run a recursive depth-first search starting from vertex A, we first set up two structures. We create an empty set to record which nodes have already been visited, so we do not revisit them or get stuck in loops. We also create an empty list to record the order in which nodes are visited. Together, these let us track the progress and final path of the recursive depth-first search. We run a recursive depth-first search starting from node A, using the Python call stack to manage the traversal. The function takes node A, a set of visited nodes, and a list that records the visit order. It marks A as visited, adds it to the order list, and then recursively visits each neighbor that has not yet been visited. In this way, all nodes reachable from A are explored in depth-first order. We start the iterative depth-first search from node A using our own stack structure instead of the program's call stack. This stack keeps track of which nodes to visit next as we explore the graph. As the search runs, we record the order in which each node is visited in a list. This record in order can then be compared directly with the order produced by the recursive depth-first search method. We first display the order in which nodes are visited using the recursive depth-first search. Then we display the visit order produced by the iterative depth-first search. Each output shows the sequence of node visits for its respective method. By comparing these two sequences, we can see how the recursive and iterative approaches traverse the graph and notice any differences or similarities in their behavior. This material explains how depth-first search can be implemented in two ways on a simple undirected graph with nodes labeled from A to F. One version uses recursion, relying on Python's call stack to explore connected nodes, while the other uses an explicit stack structure in an iterative loop. Both approaches start from node A and visit the nodes in the same order. A, B, D, E, F, C. This shows that recursive and iterative depth-first search are equivalent in how they traverse the graph, even though they manage the stack of nodes differently. DFS visit ordering. In depth-first search, the visit order shows how the algorithm explores a graph by going as deep as possible along one path before backtracking. Starting from a source vertex, it follows one neighbor after another until no new vertices can be reached, then returns to earlier points to try other options. The exact sequence of visited vertices depends on the order in which each vertex's neighbors are considered. This deep backtracking pattern produces a visit order that is different from breadth-first search, which explores the graph layer by layer. Depth-first search visit order is useful because it reveals structure in a graph. As the algorithm runs, each vertex gets a discovery time when it is first reached and a finishing time when all its neighbors have been explored. These times show how vertices are nested within each other's exploration paths. In a citation network, this can highlight chains of related papers, and in hierarchical structures, like organizational charts, it naturally groups related items and captures their nested relationships. In depth-first search, the order in which you process each node's neighbors can change the exact sequence of visited nodes, even on the same graph. If you always choose neighbors in a fixed way, such as alphabetically, the traversal becomes consistent and easier to analyze or debug. If instead, you prioritize neighbors using a heuristic, like road caucasity in a traffic network, that priority will shape the visit order, recognizing that DFS visit order is not unique, but depends on both the depth-first strategy and your neighbor ordering, helps you interpret results and deliberately control the traversal for tasks like exploring connectivity, finding clusters, or preparing for cycle detection and topological reasoning. Python code, DFS, visit ordering. This script clearly demonstrates how depth-first search visit order works by comparing different ways of ordering a node's neighbors and showing the resulting visit sequences. It is designed to help beginners understand that the order in which neighbors are processed directly affects the traversal outcome. External libraries like NetworkX, Matplotlib, and Seaborn are mentioned, but are not required for running this simple example. We represent a small graph using a dictionary as an adjacency list, where each key is a node and its value is a list of nodes directly connected to it. In this example, node A connects to nodes B and C, node B connects to D and E, and node C connects to F. Nodes D, E, and F have no further connections, so they are leaf nodes. This structure makes it easy to see and traverse all the connections in the graph. The graph is represented with a dictionary where each node is a key and its value is a list of neighboring nodes. In this example, nodes E and F have empty lists, which means they have no neighbors. This structure clearly shows which nodes are connected and which are isolated. It is a convenient way to store the graph so it can be easily traversed using depth-first search. In a depth-first search function, we keep track of the order in which nodes are visited. To do this, we create a set called visited to store nodes that have already been explored, so we do not process any node more than once. We also create a list called order to record the sequence of nodes as we visit them. Together, these structures let us efficiently manage and track the traversal process. In the depth-first search algorithm, a helper function performs the recursive traversal. When it visits a node, it first adds that node to a visited set, so the same node is not processed more than once, which prevents infinite loops. It then adds the node to an order list that records the sequence of visits. By maintaining both the visited set and the order list, the function tracks the traversal path while avoiding repeated visits. The algorithm uses a neighbor ordering function to get the list of neighbors for the current node and to decide the sequence in which they are processed. It then goes through this ordered list, and for each neighbor that has not yet been visited, it calls the depth-first search procedure again on that neighbor. By doing this recursively, the traversal continues outward from each newly discovered node. This approach ensures that every node is visited once in the specific order defined by the chosen neighbor ordering strategy. The function starts by calling an inner recursive helper that begins a depth-first search from the chosen starting node. This helper visits connected nodes, marks each one as visited, and records the order in which they are reached. After the traversal finishes, the function returns the list of nodes in this recorded order. This result shows the exact sequence in which nodes were explored during the depth-first search. This function controls the order in which neighbors are visited during traversal. It receives a list of neighbors and returns them exactly as they are, without any reordering. As a result, the depth-first search visits neighbors in the same sequence they appear in the graph's adjacency list. This preserves the original ordering defined in the graph's structure. This part of the code defines a function that takes a list of neighbors and returns a new list with those neighbors sorted in alphabetical order. By arranging them this way, the code ensures a consistent and predictable order when visiting nodes. This is especially important for algorithms like depth-first search, where the order in which nodes are visited can influence the result. We perform a depth-first search on the graph starting at vertex A, using a function that records the order in which each node is visited. The neighbors of each node are explored in the same order they appear in the original adjacency list, without any reordering. This produces a specific visit sequence, which we store for later use. We will then compare this original visit order with the orders produced when the neighbors are arranged differently. We perform a depth-first search on the graph starting from vertex A, and we always visit each vertex's neighbors in alphabetical order. Before exploring from any vertex, we sort its neighbors alphabetically and then follow them in that sequence. This gives us a consistent and predictable traversal, so repeated runs of the algorithm produce the same visiting order. The final sequence of visited vertices is recorded as the alphabetical traversal order. This code prints the order in which nodes are visited during a depth-first search when neighbors are explored in their original order. It shows how the visit sequence depends on the order in which neighbors are processed. By displaying this sequence, the code makes it easy to compare with other ways of ordering neighbors. This highlights how different traversal strategies can change the behavior of depth-first search. The code prints the order in which nodes are visited during a depth-first search when neighbors are processed alphabetically. Using alphabetical neighbor ordering makes the traversal sequence predictable and repeatable. This output demonstrates how changing the neighbor processing strategy can alter the depth-first search visit order. It highlights that the choice of ordering provides a deterministic way to explore the graph and affects the resulting traversal. This script shows that the order in which depth-first search visits nodes depends on how you choose and process each node's neighbors. It uses a simple graph stored as an adjacency list and a depth-first search function that records the visit order. One version follows the neighbors in the original list order, while another version first sorts the neighbors alphabetically. When both start from node A, they produce different visit sequences, illustrating how neighbor ordering can change the traversal path in depth-first search. DFS cycle detection. Depth-first search is useful for finding cycles in a graph because it follows one path as far as possible before backtracking. As it visits vertices, it builds a discovery tree by linking each new vertex to the one it came from. If it later encounters an edge that leads to a vertex already discovered in a different way, this suggests a cycle. In graph terms, such a cycle means there are multiple routes connecting the same set of vertices, like a loop of people who each know the next person and eventually connect back to the first. In depth-first search, each vertex can be unexplored, currently on the active search path, or fully processed. A cycle is detected when the search follows an edge to a vertex that is already on the active path, creating a loop. In an undirected graph, you must distinguish a simple backtrack to the parent from a true cycle that involves multiple vertices. In a directed graph, you must ensure the directed edges connect in a way that forms a consistent loop, such as a circular dependency among tasks. Depth-first search is a key method for detecting cycles in graphs that represent constraints or dependencies. In project management, a cycle in the task graph exposes a contradiction where tasks indirectly depend on their own completion. In software engineering, finding cycles in module import graphs helps prevent infinite loops. In logistics, cycles can reveal feedback loops or redundant paths, and detecting them helps distinguish useful redundancy from harmful dependencies. By examining the depth-first search tree and its edges, you can both confirm that a cycle exists and identify the exact elements involved, which supports effective debugging and optimization. Python code, DFS cycle detection. We will use depth-first search to detect cycles in both small, directed, and undirected graphs. During the search, if we encounter a neighbor that is still active in the current recursion path, this tells us a cycle is present. We will highlight these moments in the traversal to make it clear when and why a cycle has been found. For each example graph, we will then print a clear message stating whether a cycle exists or not. The commented line mentions installing the NetworkX, Matplotlib, and Seaborn libraries, but also explains that they are not required to run this script. This means the script is self-contained and does not depend on external tools for visualization or graph manipulation. As a result, it remains simpler and more focused on illustrating the core logic of detecting cycles in graphs. We represent a simple directed graph using adjacency lists stored in a dictionary, where each node maps to a list of nodes it points to. In this example, node A points to B, B points to C, and C points back to A, forming a cycle. Node D points to C, but does not create a new cycle by itself. This structure makes it straightforward to traverse the graph and detect cycles using depth-first search. In this example, we represent a simple undirected graph using adjacency lists stored in a dictionary, where each node maps to a list of nodes it connects to. Node A connects to B and D, so there are edges between A and B and between A and D. Node B connects to A and C, forming another edge between B and C. Node C connects only to B, and node D connects only to A. This structure makes it straightforward to move from node to node and analyze properties of the graph, such as whether it contains cycles. To detect cycles in a directed graph, we use depth-first search along with a simple color system to track each node's state. Every node starts as white, meaning unvisited. When we begin exploring a node, we mark it gray to show it is currently in the recursion stack. Once we have fully explored all its neighbors, we mark it black. A cycle is detected whenever the search encounters a gray node again, indicating a back edge to a node that is still being processed. In the recursive helper function for cycle detection, we first mark the current node as gray to show it is being visited. We then check each of its neighbors. If a neighbor is also gray, we have found a back edge and therefore a cycle, so we return true. If a neighbor is white, meaning unvisited, we recursively call the helper on that neighbor and return true if a cycle is found there. After all neighbors have been explored without finding a cycle, we mark the current node as black to indicate it is fully processed and return false, meaning no cycle exists along this path. To detect cycles in a graph, we run a depth-first search starting from every node that has not yet been visited, which ensures we cover the entire graph, even if it is disconnected. For each such node, we check whether the search from that starting point uncovers a cycle. If we ever find a cycle, we immediately return true, meaning the graph contains a cycle. If we finish exploring all nodes without finding any cycles, we return false, meaning the graph is acyclic. To detect cycles in an undirected graph, we can use a method called parent tracking. We start by defining a function that explores the graph while remembering which node we came from. As part of this process, we maintain a set of visited nodes so we know which ones have already been explored. This prevents us from revisiting the same node unnecessarily and ensures each node is considered only once during the search. This function uses a recursive depth-first search helper to detect cycles in a graph. It first marks the current node as visited, then checks each of its neighbors. For any neighbor that has not been visited, it calls itself recursively with that neighbor and treats the current node as the parent. If any recursive call reports a cycle, the function immediately returns true. If it finds a neighbor that is already visited and is not the parent, it also returns true. That also indicates a cycle and it returns true. If none of these checks find a cycle, the function returns false. To detect cycles in an undirected graph, we run a depth-first search starting from each node that has not yet been visited, so that all disconnected parts of the graph are checked. For each such node, we call a helper search function and pass along a parent reference, which is initially set to none. If this helper ever reports that it has found a cycle, we immediately conclude that the graph contains a cycle. If we finish exploring all nodes without detecting any cycles, we conclude that the graph is acyclic. We first run a cycle detection function on the directed graph, which uses depth-first search with color states to determine whether any cycles are present. We then print a message summarizing whether a cycle was found in this directed graph. Next, we run a separate cycle detection function on the undirected graph, which also relies on depth-first search but keeps track of parent nodes to spot cycles. Finally, we print another message indicating whether the undirected graph contains a cycle, giving a clear summary of the results for both types of graphs. This script shows how to detect cycles in both directed and undirected graphs using depth-first search. In the directed graph, it uses a color coding technique to track node states and identifies a cycle when it revisits a node that is still active. In the undirected graph, it tracks each node's parent so it does not confuse the edge back to the parent with a real cycle. When run, the script reports that the directed graph contains a cycle, while the undirected graph does not, and clearly prints these results. Traversal Complexity Insights, OV plus E. When we say that breadth-first search and depth-first search run in time on the order of V plus E, we mean their running time grows with the number of vertices and edges in the graph. These algorithms visit each reachable vertex once and examine each edge once, without extra unnecessary work. The V part of the cost comes from touching every vertex, and the E part comes from scanning all the edges. This gives a clear picture of how their running time increases as the graph becomes larger and more connected. The time complexity of breadth-first search and depth-first search is linear in the number of vertices and edges, because each vertex is processed only a constant number of times, such as being added to and removed from a queue or stack once. When a vertex is processed, the algorithm scans through its adjacency list exactly once, so each edge is examined only a constant number of times. This means the total work done on vertices is proportional to the number of vertices, and the total work on edges is proportional to the number of edges, with no nested loops over all pairs. As a result, if you double the number of vertices and edges in a graph, the work done by these algorithms roughly doubles instead of growing much faster. The space complexity of breadth-first search and depth-first search follows the same pattern as their time complexity, because both must store information about all vertices and edges. The graph representation itself, such as an adjacency list, already uses space that grows with the number of vertices and edges. On top of that, these algorithms keep extra data like a visited set, a queue or stack, and sometimes parent pointers, which also grow in proportion to the graph size. As a result, if you have enough memory to store the graph, you can usually run these traversals without needing much additional space, which helps you judge whether a graph problem is practical for your system. Efficient visited tracking. When analyzing the time and space complexity of breadth-first and depth-first traversal, it is crucial to keep track of which vertices have already been visited. This prevents cycles and repeated exploration, so each vertex is processed only once. By marking visited vertices, every vertex and edge is handled a constant number of times. As a result, the complexity can be expressed cleanly in terms of the number of vertices and edges without extra cost from redundant work. To keep graph traversal efficient, we need a visited structure that lets us quickly check and mark whether a vertex has already been processed, so each vertex is handled only once. You can think of this like a social network, where we must rapidly determine if a user has been seen before. If we relied on a slow method, such as repeatedly scanning a list, the time complexity would grow much worse. Choosing an efficient visited tracking structure is therefore essential for preserving the algorithm's overall performance. Efficient tracking of visited nodes is essential for controlling space usage in graph traversals. In both breadth-first and depth-first search, we store a simple visited marker for each vertex, so this memory grows in direct proportion to the number of vertices. Along with this, the queue or stack used to manage the current exploration frontier also contributes to space complexity. Together, these factors mean the total space used grows with the size of the graph and the active frontier. By managing these structures carefully, the algorithms can handle large graphs without unexpected spikes in resource use. Python code. Efficient visited tracking. We want to show how to track visited nodes efficiently during breadth-first and depth-first search. The focus is on comparing a fast visited structure based on a set with a slower approach that uses a list. By contrasting these two methods, we can see how the choice of data structure affects the number of operations needed. This, in turn, reveals the impact on the overall speed and efficiency of the traversal. The commented line mentions installing 3 libraries, Networks, Matplotlib, and Seaborn, but explains that they are not required for the simple example in the script. This means the code is designed to run without these extra tools. The focus is instead on illustrating how to track visited nodes efficiently during graph traversal. In other words, the example keeps dependencies minimal so learners can concentrate on the core concept. A graph can be represented using a dictionary where each key is a vertex and its value is a list of neighboring vertices. This structure, called an adjacency list, efficiently captures connections, including cycles between nodes. For example, one vertex might connect to several others, and those vertices can connect back, showing bidirectional links. This compact format clearly shows how nodes are related and is well suited for traversal algorithms, such as breadth-first search and depth-first search. This breadth-first search function uses a set to efficiently track which nodes have been visited. It relies on a queue structure to manage the nodes to explore, starting from an initial vertex. Each time a node or one of its neighbors is checked, a counter is incremented to record how many visited checks are performed. Nodes already in the visited set are skipped, while unvisited neighbors are added to the queue for later processing. In the end, the function returns both the total number of visited checks and the order in which nodes were visited, showing how effective the set is for tracking progress. In this version of breadth-first search, we use a simple list to track visited nodes, which is intentionally less efficient. We import a double-ended queue to manage the frontier, start it with the initial node, and keep a counter that records how many times we check whether a node is in the visited list. Each time we remove a node from the queue, we increase the counter by the current length of the visited list to reflect the cost of a membership test. Then either skip it if it was already visited or add it to the visited list. For every neighbor of that node, we again increase the counter by the length of the visited list and add the neighbor to the queue only if it has not been visited. When the queue is empty, the function returns both the total number of visited checks and the order in which nodes were visited. We compare 2 versions of breadth-first search that both start from vertex A. One version tracks visited nodes using a set, and the other uses a list. Each version reports how many membership checks it performs and the order in which nodes are visited. By comparing these results, we can evaluate the efficiency of using a set versus a list to track visited nodes during the traversal. We compare how breadth-first search behaves when tracking visited nodes with different data structures. First, we print the order of nodes visited when using a set, which efficiently records which nodes have already been explored. Then, we print the order when using a list, which is less efficient and can lead to different traversal behavior. We also estimate how many membership checks are performed with a set, showing its lower cost for these operations. Finally, we estimate the membership checks with a list, which usually requires more work, highlighting the performance impact of choosing a less efficient structure for tracking visited nodes. This material compares using a set versus a list to track visited nodes during a breadth-first search on a graph with cycles. In the first version, a set is used, so checking whether a node has already been visited takes constant time. In the second version, a list is used, which makes each membership check take time that grows with the size of the list. When the code runs, the set-based search performs far fewer membership checks than the list-based one, showing it is more efficient. Both methods still visit the nodes in the same order, but the set approach is computationally faster. Disconnected graph traversal. When we analyze the complexity of breadth-first search and depth-first search, we often assume a single starting point that eventually reaches every vertex, but real graphs may be disconnected. In such graphs, running one search from a single vertex only explores its own connected component and leaves other components untouched. To visit the entire graph, we run a loop that starts a new breadth-first or depth-first traversal from each unvisited vertex. This guarantees that all components are explored and leads us to ask whether this repeated process changes the overall time or space complexity of the algorithm. In a graph with multiple disconnected components, breadth-first search and depth-first search still process each vertex only once and examine each edge only a limited number of times. The outer loop just checks whether a vertex has already been visited, which is a quick operation. As a result, the total work remains proportional to the number of vertices plus the number of edges. This means the time complexity does not grow beyond the connected case. Even though the search may restart from several different starting vertices. For disconnected graphs, the space complexity of breadth-first search and depth-first search is still straightforward. Both algorithms use a visited structure that grows with the total number of vertices. Breadth-first search adds a queue, and depth-first search adds a stack, or recursion. But these only store active vertices from one connected component at a time. So the memory use is driven by the largest component, not by how many components there are. Overall, the space complexity remains linear in the number of vertices, and when you include the adjacency representation, it is also linear in the number of edges, with disconnection affecting only constant factors, not the overall complexity. In this lecture, you learn to implement BFS and DFS traversals on graph structures in Python. Apply BFS to find shortest paths in unweighted graphs and DFS to explore connectivity or detect cycles. Thank you for your attention. See you all in the next lecture.